Okay, hello. In this video, we will try to get into the details of transformer. Especially the encoder part. We'll have a separate video on the decoder part. And what we need to understand that how the mathematical operations are happening at the low level, so that we feel more comfortable with the actual code implementation. And if we need to modify the code, we can do it much more confidently if we understand what's happening under the hood. So we will dive deep into the transformer encoder part. So as you know, transformer has an encoder and decoder. So first of all, we need to focus on the encoder. So let's try to give some overviews on transformer. So it has been said that it is faster than LSTM, or the traditional recurrent neural network model that we are often familiar with. It can take the entire sequence or sentence as input, rather than passing the components of a sequence, for example, word by word. Or if you're feeding it a time series data, instead of feeding one time at a time for your training purposes, like we do in recurrent neural network or LSTM, here we will see an example that we can feed the entire sequence at a time, and we can learn the relative importance of the words or the tension of individual words as it relates to other words in a sequence, right? And it brings the attention mechanism in feature space, which is a very powerful mechanism. It has been the kind of state-of-the-art, giving state-of-the-art performance in many AI and machine learning or deep learning models. We will look into the mathematical operations that we need to attain this attention mechanism. And both positions, so this is something useful, interesting. So here, we are also leveraging the position information of the words or the components in a sequence. This is the positional encoding part we have. And we're kind of modulating the input vector with the positional code, so that our feature space is also aware of the relative position of the word in a sentence. For example, if I use the same word in the beginning of the sentence, that means completely different if the word is used towards the end of the sentence. So that's why the position information is very important to encode the feature, get to the feature space, as well as we are also gathering the importance of individual words with respect to other words in a sequence, right? And both of them are taken into consideration to come up with a feature space or word embedding that is much more contextual and much more meaningful and powerful than what we have seen just using word2vec or Glovi or fast text type of models, okay? And what it has been told in the literature that when you stack these autoencoders on top of other, this stacking concept is used to build up the state-of-the-art BART model in NLP. Some of you are familiar with BART model, but we're not getting into the BART model. But just to give you a heads up, the transformer autoencoder is the building block of this BART model, right? As well as transformers these days are yielding state-of-the-art performance in NLP and many different applications. So let's look into this transformer layer. So this box we have, this enter box we have here is the transformer layer, and we would like to dive deep into the mathematical operations what we have. So for now, we'll be ignoring the positional encoding part and input embedding part. Let's say we just have an input X over here. We're just feeding the input embedding to this layer, to this black box, and that X has M dimension as M rows and DK columns. So here, the DK is the D-dimensional word vector. As you know, each word is represented by a D-dimensional numeric feature vector. And here M is actually the sequence length, or the number of words in a sentence. So in a sense, X is representing one single sentence or one single sequence at a time. So as you can see, instead of feeding one data at a time, we're sending the enter sequence or the enter sentence as our input data matrix X to this model, right? And then we have to define these three matrices, the Q matrix, which is called the query matrix, the K matrix, which is called the key, and the V stands for the value matrix. So the first thing we do is we have this trainable parameter WQ, which has a dimension dk by d. So what it's doing is it's transforming the dk dimensional feature vector of X to something lower dimensional feature vector D, right? So once we do this type of transformation, we get a new feature space. So we get a feature space for Q. We are calling this is the query feature space, and this is what we are calling the key feature space. And the same thing. So the dimensionality of WK is the same as dimensionality of WQ. It's a dk by d, projecting dk dimensional feature vector to a possibly potentially low dimensional d dimensional feature vector. All right. So the end result of this matrix multiplication is Q and K, and their dimensionality is m by d, as you can imagine. So for each m words, each row, that means each m word is now represented by a d-dimensional feature vector. Okay, and then what we do is kind of interesting, and that's the attention part we're trying to get into. What we do is we take a product of these Q and K. So as you know from linear algebra, in order for us to do this product, we have to take a transpose of this K matrix, and we Q K transpose, and if we just replace Q and K with all the elements, this is the Q part and this is the K part. And as you know, transpose of this one will swap the matrix position and have transpose on individual of these matrices. So this W is essentially the product of these two, and we are considering this W as a simple W. So essentially what we have here is a kind of a inner product between input X and the transpose of the X. Right? And this is a kind of simply an inner product of the input X space, right? So once you have this inner product, what we have is an m by m dimensional P matrix, right? This is the first starting point of the attention matrix. We'll need to understand this P matrix in further details, right? Let's look into the P matrix. So if you look into the P matrix, it's an m by m. Let's say in a sentence you have 4 words, I live in Nashville, I live in Nashville. What this 4 by 4 or m by m matrix does, that at the diagonal, it will have some values that are relatively higher. That is kind of showing the relative importance of a word with itself, right? So understandably, the values at the diagonal will be relatively higher. However, the non-diagonal values sometimes will be higher, sometimes will be lower. And if it is a higher, that means we're also capturing the importance of one word with respect to other word in the same sentence, right? So number one, we're getting the importance of each word in a sequence or in a sentence from this P matrix. Number two, how each word is important to other words. And number three is we're also measuring some sort of attention of each word in a sentence, right? And then what you do here, that you have to normalize this P matrix, the entries of this P matrix with the square root of dk. Remember what dk was? Dk was the dimension of the word embedding or the word vector of our input data X. If you can go back to the previous slide, you can follow from that. So once we normalize this matrix with the square root of dk, then we take a softmax. And the result of the softmax, as you know, is a matrix where we have all the entries in the matrix with probability scores. So let's say if there are some values, for example, 2.7 or 7.3, we are scaling it down to some probabilistic scores between 0 to 1. So that, let's say, in terms of I, what are the relative importance of other 4 words, right? And one of the things we can do using applying softmax is once you take the sum of all these scores, that should add up to 1 In that way, I'm trying to understand the importance of I, or the distribution of the importance of I across all other words in a particular sentence. So each word or each row, that means each word meaning each row in this matrix, for each row, we have sum of all the columns. So we have a sum of all the columns, and that should add up to 1. So in that way, I know the weight of individual other words in terms of a given word, okay? So this is what you can see here. The importance of weight of I in terms of I is 0.6. For I and live, it's 0.1. And if you add them all up, it should be 1. And that's the beauty of using softmax, because in that way, it not only normalizes, it makes sure that when you add up the weights for one particular row or one particular word, it adds up to 1 very nicely. Okay, so let's move on. We have Q, K, and V matrices. Then we have the V matrix. V matrix is the value matrix. So the dimensionality of the V matrix, as you can see here, how would you obtain V matrix? You just take your input data X, which was over here, and you project it onto this W, V, right? So this WV is dk times dV. Once again, here we are projecting a relatively higher dimensional dk feature vector to dv dimensional. And that's why each of the m words is now in a new feature space, dv dimensional, okay? And then what you want to do is you have this, the good old P matrix. After passing it to the softmax, you do a matrix multiplication between this V with the P. So essentially what we are doing here is we're injecting or fusing the attention information that we found in this P matrix into the value features. So this A matrix, after the multiplication of these two matrices, would look something like this, right? So this is the attention map we're learning from the P, right? We saw this example in the previous slide. And then we're injecting or projecting the data, the value, feature value data, onto this attention map to be able to get the final attention A matrix. And as you can see, the dimensionality of A matrix will be M times dV. So here, each of the M words will be represented by a dV dimensional feature vector. But the good news here is you're also injecting or infusing the attention information by using the score, the relative importance score, through this matrix multiplication. So that's the beautiful part of having the attention matrix A. Okay, so each of the M words is represented by a dV dimensional attention aware feature. Okay, that's the beautiful part of it. So this A is the output of a single head. Okay, so what would be the next step? So this is the single head. So let's say we have an input X. We have an input X, and we feed into one attention head, we get one A output. In that way, we can have, let's say, K number of parallel heads, right? And these heads are independent. So what this head is doing, it's simply taking, each of this head is simply taking X and producing the A matrix. So if we have K of these heads in parallel, like this way, we will have K of these attention matrices. And that's why this module is called a multi-head attention, because it doesn't have just one head module, it has multiple head module in parallel to which you are feeding the input X. Okay, here, let's say the traditional good old paper on the model used the value of K 8. That means you can have 8 of this module and you have. So what is the next step from here? So we have to concatenate the multiple head attentions in a list. In Python, you can create a list, And heads independently examine attention at different parts of the input sequence. So each of these head will be looking into different part of the input sequence, attention in each of the different part of the input sequence. And as you can understand, the more head we incorporate, it is kind of an ensemble approach. The more heads you have, then more attention you're trying to study. By attention, meaning that we're putting more emphasis on how one word is being paid attention to the other words in a sequence. And more heads will provide more attention in understanding how the words in a sequence are related, and that will lead us to more powerful representation of the model or the feature space, right? So let's move on from here. So we have, let's say, K of these heads, and we're saying that 8 of these heads. So this is the output of the first head. This is the output of the second head. In that way, this is the output of the Kth head, let's say the 8th head. And then what we do is we concatenate them. And if you concatenate 8 of these A matrices, your dimensionality looks something like this: M times K times dV, because dV was the dimension coming from each of the head. We have K of this head, so it's going to be M times K times dV. So that's the feature representation for each of the M words coming from the concatenation of the head attention. So at this point, this A is the output coming from here, right at this point over here. So we're right at this point. We need a long way to go, right? So together, K times dV, we're calling it a D model. So D model is a model parameter you have to input when you are building one of these transformer encoder models. So we are calling it D model, and the good old traditional paper, that paper used K number of heads, K8, and 64 as dV. In together, we have a 512 dimensional D model, right? Just to give you some concrete numbers to understand what are the typical standard numbers used in that particular case. Then what you do here is you pass it through a linear or dense model. In PyTorch, we call this model linear. In TensorFlow, we call it dense, right? So it's a kind of a linear projection followed by ReLU activation. You all know this thing. And for that reason, you need to have a trainable weight matrix. And that purpose of that weight matrix, it's going to map this D model dimensional feature back to the DK dimensional feature, right? Because remember, our original data matrix has a DK dimensional feature vector. So as you can see right here, after this, we're going to have the output Y, which will be M times DK. And if you imagine that multi-head attention is a module, is a block, then the input to that block is X. The output of that block is Y. That should be pointing over here, okay? So just to compare, this has the same dimension of our input X. This is kind of interesting because in order to get it to the same dimension, we had to use this linear block to project it back to the same dimension through a feed-forward network, okay? Let's move on, okay? So now we have, you see this feedback link. So this link is getting us the actual X over here, okay? And what we're trying to do here is this part is the output of the Y output that we saw in the previous slide of the multi-head attention model. We're just summing them up, right? And that's why you have this add per. We just sum them up. And then what we do is we do a layer-wise normalization. We will talk about layer in a bit. Then because every time you add something to a variable, the scale goes up. And to keep the scale back to its original form, we have to normalize. So the consequence of this adding is the scaling goes up, and that's why you have to use some sort of normalization. And that's the norm part, as you can see over here. Okay, so adding, basically the summation operation scales up the feature space, and that's why you need to normalize, right? So this is the result, as you can see over here. you get after adding and normalization. Okay, so you take the raw input X, you take the output of the multi-head attention model, sum them up, normalize, you get the output over here. And we're calling this output just simple Y. Okay, so as you can see, after this addition and normalization, our Y will still have a dimensionality M times dk, because as you know, the dimensionality of our input was M times dk, and the dimensionality of this one was also M times dk. We showed this thing in the previous slide. So hopefully we can comfortably add these two together to be able, and then normalize to be able to come up with a Y, which is also M times dk. Okay, so now we have Y M times dk. This will be fed into a neural network. This is a feed-forward neural network with two hidden layers, right? So the first hidden layer, we call it dense from TensorFlow background, or we can call it linear with ReLU from PyTorch background. So the first dense layer or the first hidden layer will project or transform this dk dimensional feature to a higher DFF dimensional feature. DFF stands for the dimension of the fully connected layer, of the feed-forward, feed-forward layer. And typically people use this as 2048. Okay, so after this one, you will get some data, which is of what? M times 2048 dimensional. So that's the purpose of this dense layer. So once you have a dense layer, don't forget to put a ReLU on top of this matrix multiplication. You're multiplying this guy with this guy, and you have a bias term, and then you put a ReLU. That's the output you get after the first dense layer. In the second dense layer of this feed-forward network, we transform this 2048 dimensional back to our good old dk. So it's kind of a expanding the feature dimension and then compressing it back to our good old dk dimension, right? So finally, after passing through this feed-forward neural network, we have a Z. So Z is the output coming right over here. That's the Z, output of the feed-forward network. And the dimension of Z would be, once again, M times dk. dk is the dimension of the feature vector of our original input data, right? So where do we go from there? As you can see, this add and norm module we have here, the same add and norm module we have here. So what you have to do is you have to add this guy. As you can see, you have this feedback loop. Add this guy with this guy, and then normalize, right? So if we move on to next step. So before we move on to next step, just to let you know, this entered thing is basically the feed-forward fully connected layer where you have two hidden layers. This is the first hidden layer. This is the second hidden layer. Okay, so now we have the Y, and now we have the Z in the previous slide. What we do here, Z is the output of the fully connected layer given input Y, plus we're adding Y. We're adding Y here, right? So here we have Y, and here we have Z, which is the output of the input Y to the fully connected layer. So you just add them up, simple adding, and then you have to do layer-wise normalization, because every time you add, the scale goes up. You have to keep the scale back to normal. That's why you have to normalize. So finally, what you get is the Z feature space of layer 01. Right? So this is a layer 01. And now you notice that there is a term here, n times. That means this block can be repeated, can be cascaded n times. And every time it receives an input, it gets you the Z. So what is the, if we consider this is just a layer. So this is my layer. So input to this layer is this X, good old X. And what is the output to this layer? This Z. So I'm denoting 01 to represent the feature embedding from the layer 1. Then what do? You just take this feature embedding and put another layer of encoder, where you have the same multi-head attention and you have the same feed-forward network, right? So This is your Z01 output from the first layer will be fed into the second layer, and that will give you what? Z02. That is the output of the second layer. So in the literature, you will find number of layers. People are considering 6, just to give you a number that you can choose. And if we sum up the whole thing, the multi-head attention, we can imagine this is just a model that takes these following parameters. K is the number of heads you need to form this multi-head attention. D model, remember D model was a parameter we defined, which was K times dV. And D was the dimension of the Q matrix and the K matrix, and dV was the dimension of the V matrix. Because as you can see, these 3 arrows are suggesting that you have to deal with the Q, you have to deal with the K, and you have to deal with the V separately. Although we are taking a product of Q and K to be able to get the attention information out of that. So if this is the model, the multi-head attention model, and that gives us Y, then what would the model, the enter model, this is the enter layer, right? We call this enter thing block as a layer. So these are the parameters this layer will be taking. Number 1 is the D model. You know what a D model is. Number of attention heads, as well as the DFF. Remember, we had to use this DFF in one of the hidden layers in the feed-forward network. So that's the, remember the 2048 number. So that's the DFF, the dimension of the hidden layer that we need to have to build just one of these layers. And as you can imagine, one of the things we can do is we can stack each of these layers. So the input X is getting into layer 1, we get the output Z1 that is fed into layer 2. So what you do is you take a copy of this thing and cascade it on top of other. And finally, after 6th layer, you get the Z6. Now, just to remind you, the dimension of the Z6 will be good old dk. So as you can see, we are fitting in X, which is m times dk. That means m words, each represented by a dk dimensional feature vector. And this X is going through so many mathematical operations through the addition from multiple layers, from the attention information from multiple heads. And finally, it's producing a new feature space, which is also m times dk dimensional, right? But the good thing about this Z6 that it has much stronger or much more powerful information about the attention, about the relative importance of the words as they are placed or as they're sequenced in a sentence. On top of that, we also have this positional encoding is being injected. So positional encoding will need a separate slide, as you can imagine. So this is the output of a transformer encoder, right? And once we have the output from a transformer encoder, what do? The next part is the decoder part. We feed this final G6 to the decoder part, and the decoder part will need me to create a separate video, and then we can go and try to understand that part and the interaction between encoder and decoder in further details. Thank you.